Hello, and welcome to the 5th episode of SolTouch. Today we're going to talk about tests, and we're going to see how truffle tests can actually help us to create a better contract and better code. In Solidity, you basically write a lot less code than you should write for tests. So your smart contract may have, like this example of ERC20 contract, a couple of lines, and the tests that follow can actually be some substantial amount of code. That is because when you develop in Solidity, you want to write as many tests and to have as much coverage as possible, and that's partially because blockchain is immutable, and partially because even if you use a proxy, it will be a nastier process to upgrade your contract in case of a bug. So let's start by discussing a little bit what we prepared for this tutorial. We have here a simple ERC20 contract, which is something called MetaCoin, which handles meta tokens. In this contract, we can see that we inherit from ERC20, the standard created and implemented by OpenZeppelin. We inherit from ownable contract, which is yet another OpenZeppelin library that specifies the owner of a contract. And we do the following things. In the constructor, we first mint 10,000 tokens for the owner, for the sender of the constructor transaction, basically. We have a mint function, a burn function, and a mint reward function. We can see here that the mint function and the burn function is only called by the owner. So let's look a little bit at what mint reward function does. First of all, it checks if 1 day is elapsed from the time set in the last mint variable. Here time is specified in seconds, so 86,400 should be more or less 1 day. After we pass this require, we save the timestamp into the last mint variable, and then we mint 1000 tokens for the caller of this function. So this is the contract that we're gonna work with today, and we're gonna start by passing through some already implemented tests, and also we're gonna write some special test which encapsulates much of what a Solidity developer has to do in the testing phase. If you're working with Truffle Suite, you're gonna find your tests in the test folder. You're going to create another file, or if you would prefer to have a more modular structure, especially if you have a lot of contracts, you can create different folders, different files here, and you can use them all. But for today, we're just going to use this file, and we're going to create some tests here. Good. So how do we test? Basically, what happens when you run the testing command, which is npx truffle test, you work with the development network that you specified in truffle config. So right now, in truffle config, we have the port and the network ID from Ganache. So our testing will be done with Ganache. If I run this command, I receive this error because right now Ganache is not opened. So we're gonna have to open Ganache and create a development network for testing purposes. We don't need anything fancy, so we're going with the quick start network. The network ID and the port are found here. They're properly set up, and right now we're gonna see if we get some tests or still an error. So the tests pass correctly, and now let's dive a little bit into what we are testing here. When you write tests, you should first write a proper description for them. So you should, in short, tell the other programmers or whoever is reading the code what the test should do. In our case, with this test, we verify that indeed when the constructor is called, we have 10,000 metacoin in the account that deploys the contract. For this, we need to know who deploys the contract, and we need to know which account does that. And we're going to find this out in truffle deploy. We see that we have no account specified here, so we can specify something like accounts of one, and in this case it will be launched from the from the second account, from the accounts variable. If we leave it empty here, the contract is launched by default from the accounts of 0. So this one basically. Now we need to find out the balance after a contract was deployed. We need to find out the balance of this account, and in order to do this, we call the balance of function. Whenever we have read functions, we use .call for that. If we have functions that modify the internal state of the contract, we just call them directly by name and do not use call. For example, here we call a transfer and we do not use .call. One important aspect is that the .call function does not take up any gas, so basically you just read from the contract and the transaction doesn't cost anything. So here we interrogate the balance, we return the promise of this function call, we grab the result from here, and we do an assertion. Assertions are basically what you expect to find out or to happen in the contract. So when we use assert.equal, we basically check that the first and the second parameter are equal. And in the case in which they aren't equal, we throw this error message. So what about this second test? This second test is actually quite the same as the first test. So functional is the same thing. We verify that the balances are equal, but here we do an asynchronous test. So in order not to work with promises in a more complicated manner and to use .then and so on, we keep it a little bit more simple. We do the test asynchronous and use awaits. So you can start writing tests in any of these two manners. I personally prefer to do it asynchronously and use await because it's a little bit cleaner in terms of how the code looks and more simple to read, to be read by another developer. So basically we wait for the contract to deploy and then we save it in the meta variable. We wait for the balance of call to happen and to interrogate the balance of this account. And then we go on and make the assertion and check that here we do indeed have 10,000 tokens on the first account. So that's basically another way of writing tests in an asynchronous manner. Moving on, we have a transfer test. So we need here the first account, the second account, and the amount that's gonna be transferred from one account to another. We get the balances of the first account and the second account and save them in account 1 starting balance and account 2 starting balance. We go on ahead and actually do the transfer. Here we need to pass to the transfer function just 2 parameters. That's account 1 and the amount transferred. And the contract knows who called this function by the fact that we specified here that it's called from account number 1. So the ERC20 standard doesn't need to know from who to who you transfer the tokens when you just call the simple transfer function. If we wanted to, let's say, transfer from account 2 to someone else, we would switch this and put here account 1 and account 2, and in this case the tokens flow from account 2 to account 1. After we actually do the transfer, we do some balance checks. So we look at how much money does account 1 have and how much money does account 2 have. We save them in account 1 ending balance and account 2 ending balance. And then we go ahead and do our assertions. So basically what we expect here is that the ending balance of the first account should have less money than the starting balance with the exact amount that we transferred. So we just check that account 1 ending balance equals to account 1 starting balance minus amount transferred. Same for account 2. We check that the ending balance is equal to this time account 2 starting balance plus the amount transferred, and that's how we do this transfer test. We introduced one more test here that checks that the mint process is properly executed. So what we want here is to mint 10,000 tokens. That's why we save them in this variable. We go ahead and actually call the mint with the amount of tokens required, and we need to make sure that the function is called by the owner of the contract, and by default we have seen that the owner of the contract is accounts of 0, this one. Then we go ahead and check the balance, and we do an assertion. We check that the minted amount is equal to ending balance minus starting balance. And we see that if it fails, we're gonna display that the amount was incorrectly minted. Good. So these are some quite simple tests. We want to go ahead and do some tests that are a little bit deeper and might not be just simple function calls and assertions. And for that, we're going to look at the mint reward function. And what we want to do is to cover basically anything that can happen and to check that our expectations are met. So what happens in this function is that we first of all check that 1 day has passed since your last mint reward. So that's one thing that we're going to want to test. Another thing that we want to test is that you actually receive the funds when you call this function. So my proposition would be to create a test where we first of all check the initial balance of an account. We call that mint reward function. We see that the balances are correctly minted by the contract on our account. Then we check that the contract actually reverts when we do another subsequent call without waiting for the 1 day to pass. And then we want to see that if indeed 1 day passes, we are allowed to call that function again. So what we're going to name this test is mint reward use cases coverage. It's going to be an asynchronous test. We will need the account with which we're working. This function isn't restricted to the owner, so my proposition would be to use account 1, accounts of 1, and we're gonna name it account 2. We also need to get a reference to our deployed contract, which will be in meta. We need to know how much tokens, how many tokens we receive when we call this function, and we can see here that it's 1000 tokens. So token reward will be a constant of 1000. Then we need to go ahead. We'll also need this balance, which is an auxiliary variable in which we temporarily store the balance of the account. This is just for aesthetic reasons, so in practice you might not want to use this variable at all and do something like this. But here I'll actually use it so the code looks a little bit prettier and it's a little bit easier to follow. So we receive the starting balance, and then what we want to do is actually call the mint reward function. So we're going to call mint reward. We can see that the function mint reward doesn't take any parameter. However, in the JavaScript, we want to specify from who we want to call this function. So I will specify account 2 here. We are also waiting for the function to finish doing what it's doing. And then we want to do the first assertion. We want to have mint reward equal to the balance of the account number 2 right after we have called the mint reward function. So we're going to get the balance of account number 2 again. I copy pasted this and forgot to change it to account number 2, and we're going to name this balance after first reward. Cool. So we want the balance after first reward minus the starting balance to be exactly 1000 or the token reward. If we're going to fail to accomplish this assertion, mint failed, mint reward failed. Okay, good. So let's run it and see if it works in this state. And there we're going to move on to the complicated part. Okay, so the test passed. Now what we want to do, is to make sure that we cannot call mint reward another time after we just called it. So we are actually going to do this, and we are going to see how the test behaves in this particular situation. Okay, so the contract reverted. It reverted with this message, but the test shows that it failed. So we do not want that. We want a nice green check mark to the tests, and we want to see it as passing test, especially because we expect this to fail. So what I'm using here is truffle assertions. It's a bit more complicated to expect for failures if you do not use a library. So we have this pretty library that we can use, and I actually recommend you to go ahead and use a library if you can do so, and if you find a nice one that works for you. So I will use this one, and what we're going to do is expect a revert. So if we call truffle assert dot reverts and place here the function, the promise to the function that we're expecting to be reverted, which is mint reward, and from account to, and the message with which the function should revert. We can get this in the contract when we watch this require. I forgot to close a parenthesis. Okay. What you also need to take into account is that this returns a promise as well. So if you want the test to go ahead and do the final assert, you might want to place a wait here. So yeah, don't forget to place that await as well. And now we're going to run the test, and hopefully it will not fail. And if it passes with success, it means that the transaction reverted with what we anticipated. So it does pass with success, and right now we have our first revert test. Good. So we're in this room now. We have tested that we get the reward on our account. We have tested that if we attempt to call a subsequent revert, we fail. And we want the use case when a day does pass and we are able to call mint reward again. Of course, we cannot wait one day for that, so we'll have to mess a little bit with the internal time of ganache blocks. So in order to do that, again, a library comes in handy, which is truffle test helpers. And what we're going to be interested in for this test is latest time, duration, and increase time too. So we first of all want to find out what time is now on the blockchain. So in order to do that, we call the latest time. This also returns a promise, so make sure if you're working in an asynchronous manner that you place an await here. And right now we got the current time of the blockchain. We want to advance to specified time. So we're going to use the current time and add to it 1 day. You can use duration to add like days, hours, minutes, and so on. For our purpose, it's sufficient to just advance the time 1 day. then what we want to do is actually increase time of the blockchain to the amount specified, so advanced to specified time. And we are also going to wait for this operation to finish. After we advance the proper amount of time, we're going to call the mint reward again. And we have seen that if we went ahead and called the mint reward right after this without reverts, without truffle assert, it simply fails. So the test will just show that it failed. We can confirm this. Yep, transaction is reverted with an ugly red error. So right now it should pass because we advanced the time of the blockchain with 1 day, and approximately 1 day is specified here. I have a typo. Okay, so now we see that this works. We can do to really make sure that it works, we can do something like advanced 23 hours, and this test should again fail. That is, if I correctly calculated the seconds in a day. So yep, it fails. We're gonna stick to 1 day, and then we're going to make another assertion. We're going to interrogate the balance again. So ending balance, we'll be calling this variable ending balance, and we're going to do another assertion. Second time. We're going to assume that the ending balance minus the balance after first reward is actually equal to token reward. We're going to run this test as well and see if everything went okay. Yes, the assertion does not fail, so we basically did it. We managed to mint the reward the second time. We managed to make the blockchain, our Ganache, our local blockchain, to advance in time for testing purposes. And we've covered some majority of the tests that you will see in practice. So basically, we have covered the tests that simply look at the value that's returned by the contract. We have seen how to expect a specific message or a specific failure, and we have seen how to tamper a little bit with the block time in order to test that something happens after a specific amount of time. So with this in mind, I think that you are ready to cover like 95%, 98% or whatever of the tests that you will be required to do in practice. One thing that I would like to mention at the end of this video is that it's very, very, very important to have good and encompassing tests when you write Solidity code. Like for 3 lines of code in the mint reward function, we have written many more lines of code in the tests, and this is a good thing. This is how contract should look. For each function that you have in the contract, you should write unit tests and the proper tests to cover all cases that the contract might encounter in practice. In my opinion, this makes the difference between basic Solidity code and quality contract. So if you really want to deliver quality, you need to step up with your testing. So you really need to cover everything, and I think this is the most valuable thing that a Solidity developer can do. You can also use your testing skills to audit other contracts. This is also encountered in practice. So I also do, for example, audits, and when doing an audit, aside from following the logic in the contract, you need to pay attention and to implement the proper tests, either to prove a bug or either to make sure that a specific scenario doesn't cause any trouble with the rest of contracts. One more thing that I also do is when I develop Solidity contracts, I write in a modular way, meaning that I create 1-2 functions, then I go ahead and write tests for them. I run the tests and make sure everything is okay. Then I go on and implement 1-3 other Solidity functions. Then I run the test again. And I do encounter situations in which when I write the third function, the tests for the first 2 functions fail, for example. And those are really the times in which I am glad that I'm working like this and implementing a function, implementing tests, and so on and so forth. Keep in mind that a mistake on the blockchain isn't the same as a mistake in a web application, and it might be immutable. And please be careful and thorough about the tests you're implementing. That being said, thank you for watching, and if you enjoy this, subscribe, and we'll hear from each other next time. Thanks.